Hello students, I welcome you in today's session of physics, and in physics you can see here I am going to present you a chapter number 25, which is the wave particle duality matter waves. You can see here this is the chapter. So before going to start the chapter, let's have a look what we have to study in this chapter. This is your syllabus. So in this chapter first we have to discuss about the dual nature of radiation, particle nature of light, matter waves, wave nature of particle, de Broglie radiation, David Germer experiment. Fine. After that, we have to cover out the experimental details should be omitted, only conclusions should be explained here. So first we have to discuss, going to discuss about the dual nature of radiation, which is the wave nature as well as the particle nature. Clear? So here it is written that the phenomena like interference, diffraction and polarization, these things we had already covered out in our previous lectures. So were explained successfully on the basis of wave nature of radiations. Clear? But these phenomena could not be explained by the particle nature, that is the corpuscle theory of light. So for example, in interference of light, two light beams meeting at some places produces darkness. But it is not possible that two corpuscles meeting at a point may destroy each other. Fine. So on the other hand, certain phenomena like photoelectric effect and you can see here the Compton effect could only be explained by the quantum theory of radiation, in which the radiation is considered as the particle nature but cannot be explained by the wave nature of radiation. So for example, if the light is in the form of wave, then on increasing the intensity of the light, the amplitudes of the waves and hence the energy accumulated in the waves will increases. Clear? So these waves when falling on the surface of the metal will provide more energy to the electrons of the metals, with the results that the energy of the emitted photoelectrons will increases. But the energy of the emitted photoelectron does not depend upon the intensity of the light. And the secondly, if the frequency of the light waves is below a certain lowest value, then the photoelectrons will not emit it. So however a large the intensity of the incident light may be, it means that the radiation has the dual nature, behaving sometimes as a wave and sometimes as a particle. So this is the dual nature of light. Now come to the particle nature of the radiation or light. You can see here this is the topic 2. So the phenomena, again that is the thing written here, the interference, diffraction and the polarization were explained successfully on the basis of wave nature of radiation. So considering the radiation as an electromagnetic waves, on the other hand, certain phenomena like photoelectric effect and the Compton effect could only be explained by the quantum theory of radiation, in which the photon effect and the Compton effect could only be explained by which theory? Quantum theory or photon theory of radiation, in which radiation is considered as the particle nature. So it means that the radiation has a dual nature, so behaving sometime as a wave and sometime as a particle. So far, no single experiment has been devised which shows dual or particle nature of the radiation simultaneously. So describe an experiment which picture where the particle or a wave is best suited depends upon the nature of the experiment. So for example, when we see an object, both the aspects are important. So the gathering and the focusing of light by the eye lens is well described by the wave pictures, while absorption of light by the retina is described by the photon picture of light. Now come to here, you can see that in 1900 Planck put forward a revolutionary idea that the emission of radiation is not continuous but takes place in the form of small bundles or packets of energy, which we call as photons. And Einstein arrived in an important result that each photon is associated with a definite amount of energy which is equals to h nu, that is E is equals to h nu. Clear? So here you can see that, and momentum which is h nu by c moving with the speed of light which is small c, where nu is the frequency of the radiation and h is the Planck constant. So the definite value of energy as well as the momentum is a strong evidence for the particle nature of radiation. So the particle like behavior of radiation was further confirmed in 1924 by the Compton experiment on the scattering of X-rays. So we may summarize the photon, that is the particle picture of radiation or light, as follow. First one, the radiation in its interaction with matter behave as if it is made up of particle called photons. Clear? Now the second one, each photon has an energy is equals to h nu and kinetic energy h nu by c squares, and the momentum is equals to h nu by c, and you know very well that is the speed of light. So however, the rest mass of the photon is 0. Now come to the third one, all the radiation of the photon of a particular frequency have the same kinetic mass, energy and same momentum whatever the intensity of radiation is. What is the fourth one? Come to the fourth one, photon are electrically neutral and are not deflected by the electric and the magnetic fields. Now the fifth one, In a photon particle collision such as photon electron collision, the total energy and the momentum remains conserved. However, the number of the photons may not be conserved in a collision. Now come to the sixth one. A photon may be absorbed by the matters and a new photon may be created. Now see the third one, which is the wave nature of particles. So in 1924, physicist de Broglie introduced a bold hypothesis that if the radiation has a dual, means wave particle nature, the moving particle of matter, which is called electron and protons, should exhibit wave-like characters under the appropriate conditions. So he reached this conclusion on the observation that the entire universe is composed of matter and electromagnetic radiations, and that nature loves symmetry. So these two physical entities, matter and radiations, must have symmetrical characters. Thus, according to the de Broglie, all the material particles in motion have wave nature also. So the waves associated with the moving particles are called the de Broglie waves. This is the most important one. Now here you can see the de Broglie wavelength of the matter waves, how we can calculate them. Just have a look. Now according to the quantum theory of radiation, the energy of the photon, you know very well, is how much? E is equals to h nu, where nu is the frequency of the radiation. So according to the Einstein mass energy relation, which is your E is equals to mc square, mass of the photon carrying energy. So from this equation we can write here m is equals to E by c square, and in place of E we can write from E is equal to h nu, so we put here h nu by c square. Clear? Where c is the velocity of the light in the free space. So the photon travel with the velocity of light, therefore the momentum of the photon is given by P is equals to mv, or in place you can write here h nu by c square multiplied by c, or h nu by c. Clear? But you know very well nu equals to c by lambda, where lambda is the wavelength of light. Therefore from this relation P is equals to h by lambda, or you can write here lambda is equals to h by p. Fine. Thus the wavelength associated with a photon is h by p. So the de Broglie postulate that the wavelength associated with a moving particle is in analogy with light, which is given by lambda is equals to h by p, where p is the momentum of the particle. Now a particle of mass m moving with the velocity v has a momentum in how much? mv. So therefore the de Broglie wavelength, which is associated with the moving particle, you can write it lambda is equals to h by mv. So in this relation, the velocity which is your v of the particle is much smaller than the velocity of the light, otherwise this relation will have to be modified. So the above relation which connects the wavelength with the momentum, a characteristics, leads to the following conclusion. The first one, if in this equation v is equals to 0, then lambda equals to how much? Comes out to be infinite. Means that the wave are associated with the moving particles only. Fine. Now the second one is the de Broglie wavelength does not depend upon whether the moving particle is charged or uncharged. It means that the matter waves are not electromagnetic in nature, because electromagnetic waves are produced by the motion of the charged particles only. Now here you can see the de Broglie wavelength for the electrons. What are the de Broglie wavelength for electrons? So let us consider an electron is of mass m moving with a velocity of how much? Small v, much smaller than the velocity of light. So its de Broglie wavelength is given by lambda is equals to h by mv. And if k be the kinetic energy of the electron, then you can write it k equals to half mv square, or you can also write it v is equals to under root 2k by m. So now put these values in the de Broglie wavelength, which is your lambda is equals to h by mv. So in place of v we can write here root 2k by m. And finally this is the wavelength for the electrons, comes out to be lambda is equals to h upon root 2 mk. This is, however, a general expression for the de Broglie wavelength of a moving particle in terms of its kinetic energy of the particle. So let us now come to the particular case of electrons. If the electron acquire kinetic energy on being accelerated from the rest through a potential difference v volt, so we can write here k is equals to ev. Fine. So where E is the charge of the electron, substituting the value of k in equation first. Here you put the value of k. So the relations comes out to be lambda is equals to h upon root 2 mev. And if we put the values, so here you can see that after putting the value, the relations comes out to be 12.27 root v under angstrom, which is root 150 by v angstrom. I hope you understand it. Now come to the experimental demonstration of de Broglie matter waves. I am not going into the very deep. This is the demonstration. So let's have a look. What is the demonstration of de Broglie matter waves? There is a scientist Davidson and Germer experiment. You can see here, this is the name of the scientist, Davidson and Germer experiment on electron diffraction. So if the material particle have a wave character, they are expected to show the phenomena like interference and diffraction. It is the wave nature of light. So in 1927, the scientists named Davidson and Germer demonstrated that the beam of electrons does suffer diffraction. Here you can see this is the figure, and with the help of this figure you can easily understood what is going on here. So their apparatus is shown in the figure. So, this is the figure. Electron emitted from a heated element, which is your F, fine, in an electron gun are collimated into a fine pencil by the perforated diaphragms and are accelerated through a variable potential V. So the electron beam emerging from the gun fall normally on a nickel crystal, which is your C. So the electrons are diffracted from the crystal in all the direction. The intensity of the diffracted beam in different directions is measured by the Faraday's cylinder, which is connected to the galvanometer, which can be moved along a circular scale S. So the crystal C can be turned about an axis parallel to the incident beam. Thus any azimuthal of the crystals can be presented to the plane defined by the incident beam and the beam entering by the Faraday cylinder. You can see here from the figure. Clear? So now here you can see these are the graphs given in the figure number 2. These are the few graphs given here. So what's going on? First of all, accelerating potential V is given a low value and the crystals is turned at an arbitrary azimuth. So the Faraday cylinder is moved to various positions on the scale S and the galvanometer current at each position is noted. Now the current which is measured of the intensity of the diffracted beam is plotted against the angle phi. You can see here from the figure. Between the incident beam and the beam entering the cylinder, the observations are repeated for different accelerating potential. Clear? The corresponding curves are drawn in the figure number 2. You can see here. So it is seen that a bump began to appear in the curve for 44 volt electrons with increasing potential, and bump increases and become most prominent in the curve for 54 volt electrons, which is phi equals to 50 degree. So at higher potential and bump gradually disappear. You can see easily from this figure. These are the figure demonstrating that. So the bump is in its most prominent states verifies the existence of electron waves. For according to the de Broglie, the wavelength associated with the electron accelerated is equals to how much? Which is equals to lambda equals to 12.27 by root V angstrom. Fine. So hence the wavelength associated with the 54 volt electron, it comes out to be lambda is equals to 12.27 root 54, which is 1.67 angstrom. Now it is known that from X-rays analysis that the nickel crystal acts as a plane diffraction grating. Now with the grating space D is equals to how much? 0.91 angstrom. This you can see from the figure number 3. So according to the experiment, we have diffracted electron beam at phi is equals to how much? 50 degree. So this arises from the wave-like diffraction from the family of the Bragg's atomic planes. The corresponding angle of incidence related to the family of Bragg planes is how much? Theta is equals to 65 degree, which is you can find out from the 180 minus, you can see here from this figure. Fine. So hence using the Bragg equation, taking the order where n is equals to 1, we get lambda equals to 2d sine theta. This is the Bragg equation, and in here you can put the value of spacing, that is your d is how much? 0.91 angstrom, and in place of theta you can write it 65 degree. So finally the value comes out to be 1.65 angstrom. So this being in excellent agreement with the wavelength computed from the de Broglie hypothesis, shows that the electron are wave-like in some circumstances. So other fundamental particles like neutron also show wave-like properties. So the Davidson and German experiment thus provided direct verification of de Broglie hypothesis of the wave nature of moving particle. I hope you understood what I taught you. This is the end of the chapter, students. We will meet with the next chapter in our next lecture. So till that, do study. Thank you, class. Thank you very much.